The force convection heat transfer. Under the action of external forces, if the fluid flows through the pipe or over a plate, the corresponding heat transfer is called as force convection. Whenever the flow is taking place over a plate, it can be divided into two parts. First is laminar, second is turbulent. Laminar and turbulent flow can be identified by using a Reynolds number, and the Reynolds number is given by a product of density multiplied by velocity multiplied by characteristic length divided by dynamic viscosity mu, and is defined as inertia force divided by viscous force. Here LC represents the characteristic length. If the flow is taking place through the pipe or through the rectangular duct or through the annulus, in that case the characteristic length is taken as 4 times area, that is the cross section area, divided by weighted perimeter in the case of internal flow. And in the case of flat parallel plate, that is in the case of flow over a plate or a cylinder or a sphere, the characteristic length L is taken as parallel to the direction of flow. The heat transfer coefficient is obtained by using the Nusselt number, which is given by H into characteristic length, which is given by same definition, divided by K, and the local heat transfer coefficient we can calculate as minus K into dt by dy at y equal to 0 divided by wall temperature minus T infinity. Two more numbers are important in the case of force convection. The first is a Prandtl number, which is given as mu Cp by K, and we have a delta T represents here the thermal boundary layer thickness, delta represents here hydrodynamic boundary layer thickness, and we have a relation between the thermal boundary layer and the hydrodynamic boundary layer thickness, and is given as delta T equal to delta into Pr to the power minus 1 by 3. Stanton number is given by the local heat transfer coefficient Hx divided by density multiplied by U infinity multiplied by Cp. Whenever the flow is taking place over a flat plate, in that case there is a development of a hydrodynamic boundary layer, and the thickness of a hydrodynamic boundary layer thickness equal to delta. U infinity is called as free stream velocity, and the flow can be modeled as U upon U infinity equal to 3 by 2 y by delta minus 1 by 2 y by delta cube. Similar to hydrodynamic boundary layer, if we have a plate which is maintained at equal to Tw, surrounding fluid temperature equal to T infinity, then we observe a temperature gradient inside this region, and that we have a temperature profile is given as T minus Tw upon T infinity minus Tw is identical to this equation, except delta is replaced by thermal boundary layer thickness, which is equal to delta T. If you want to find out the shear stress on the wall, you have to use the Newton's law of viscosity, that is mu into du by dy. Solve this equation at y equal to 0. If you assume this profile, you will get this answer equal to 3 by 2 U infinity multiplied by mu divided by delta. And just now we have seen how to find out the heat transfer coefficient. If we use the equation, in that case the local heat transfer coefficient is given as 3 by 2 multiplied by thermal conductivity of fluid divided by the thermal boundary layer thickness, and using the definition of Nusselt number, we will get the Nusselt number equal to 3 by 2 x divided by thermal boundary layer thickness. It is observed here is that delta is directly proportional to root x. Shear stress is also proportional to the reciprocal of root x, and delta in the case of this cubic equation is given as 4.64 times x upon under root of Rex. Tau w and the local heat transfer coefficient are proportional to 1 by root x. If we use the Blaise's equation, in that case we have delta equal 5 times x upon under root of local Reynolds number. For laminar flow, local Nusselt number is given by local heat transfer coefficient Hx multiplied by the distance x, which is measured from the leading edge, divided by thermal conductivity of the fluid equal to 0.332 times local Reynolds number to the power 0.5 and Prandtl to the power 1 by 3. Since here in the case of laminar flow, the average heat transfer coefficient h bar, which is given as integral of hx dx over the length 0 to L divided by integral dx from the limit 0 to L is same as L, is same as equal to 2 times of local heat transfer coefficient, or this time the heat transfer, which is calculated on the base of the total length. Therefore, we have the average Nusselt number over the length L is given by 2 times of this number, which is equal to 0.664 total Reynolds number to the power 0.5 Prandtl to the power 1 by 3. This equation is only valid for laminar flow. Stanton number, which is basically a ratio of Nusselt number divided by a Reynolds number and the Prandtl number, is same relation we have, that is equal to 0.332 Reynolds to the power minus 1 by 2 Prandtl to the power minus 2 by 3. And if we use the Colburn analogy or the Reynolds analogy, in that case we have Stanton into Prandtl to the power 2 by 3 is same as the local skin friction coefficient Cfx divided by 2. Whenever the flow is taking place through the pipe or duct, in that case we have characteristic length is given by 4 times the cross section area divided by the weighted perimeter. For a circular pipe, we have the cross section is pi by 4 into d square and the weighted perimeter is pi d. So in the case of circular pipe, we get LC equal to same as d. In the case of rectangular duct, we have 4 times cross section area is A by B, where A and B are the sides and width, divided by 2 times of A plus B, that is the weighted perimeter. So we have LC equal to 2 times of AB upon A plus B. The velocity distribution in the case of pipe is a parabolic. We have maximum velocity at center, and on the wall the velocity will be equal to 0. Here velocity u is strictly a function of radius r. The temperature distribution is also a parabola, and the temperature at any point is strictly a function of radius only. This time we have Tw is the temperature of wall and T is the temperature of the fluid at any radius r. The mean velocity of a fluid, which is the average velocity over the given section, is obtained by 2 by r square into integral of u multiplied by r into dr from the radius 0 to capital R. And the bulk mean temperature Tb is calculated based on the mean average velocity is given as 2 divided by mean velocity um into r square into integral of u multiplied by t into r into dr from 0 to r. 2 types of numerical normally occur in the case of internal flow. First is the constant heat flux, second is the constant wall temperature. The temperature distribution is shown like this. We have Tw and we have the fluid temperature will change from Ti to T0. This temperature is called as the bulk mean temperature. This time the fluid temperature will change according to the straight line. Initially up to fully developed flow, we have a variation of temperature. This time the excess temperature equal to theta and is constant value over the entire length. This time the heat transfer coefficient Hx is always constant. And according to the law of conservation of energy, we have rate of change of internal energy must equal to the heat transfer by convection. Rate of change of internal energy we can obtain as m dot into Cp into final temperature To minus initial temperature Ti equal to heat transfer coefficient H multiplied by surface area, which is pi dl, multiplied by the theta value, that is the excess temperature. This is same as the heat transfer. So we have a heat flux here, which is defined as Q divided by area, that is the surface area, is always constant, that is H multiplied by theta. Since theta is constant, H is also constant. In the second case, the wall temperature is maintained constant. So this one is representing the constant wall temperature. We have a inlet temperature equal to Ti, exit temperature equal to To. The excess temperature here continuously varies. The excess temperature at inlet is represented by theta I which is Tw minus Ti. Excess temperature at outlet is represented by theta O, which is Tw minus T0. This graph is here exponential graph. As the balance of the energy is considered, you have to use the same equation, m dot Cp T0 minus Ti. So we have Q is equal to rate of change of internal energy is m dot into Cp into T0 minus Ti. Since here the temperature is continuously vary, the heat transfer is given by As multiplied by H multiplied by LMTD. That is the log mean temperature difference. And LMTD this time is given by theta I minus theta O divided by ln of theta I by theta O. Or we can equate the theta I and theta O as an exponential distribution, that is e to the power h multiplied by surface area divided by mass flow rate m dot into Cp. For a constant heat flux, we have Nusselt number is given by Nu equal to 4.36. And in the case of circular pipe, the characteristic length is Lc is same as equal to D. So Nusselt number is given by Hd by K. K is the thermal conductivity of fluid. Whereas in the case of constant wall temperature, Nusselt number is given by 3.66. Both these equations are valid for laminar flow. In the case of turbulent flow, you have to use the Dittus-Boelter equation, which is Nusselt number equal to 0.023, Reynolds to the power 0.8, Prandtl to the power n. And the value of n you have to select as 0.4 for heating and 0.3 for cooling. In the case of free convection or the natural convection, Nusselt number is usually expressed as C times Gr into Pr to the power m. Grashof number is given by G into beta into theta, which is the excess temperature, multiplied by Lc cube divided by kinematic viscosity square. Here beta is coefficient of volume expansion, as it is given as 1 by V into the change in volume divided by change in temperature by pressure. In case of gases, beta will be same as 1 upon Tm, but you have to take Tm in Kelvin. Here Tm stands for mean temperature. The mean temperature is given as Tw plus T infinity divided by 2, but take care that it must be in Kelvin. For natural convection, laminar flow can be identified from the product of GRPR, and if we have the product of GRPR is less than 10 to the power 9, it will be called as laminar flow. In that case, you have to select the value of m equal to 1 by 4. And if the number exceeds that 10 to the power 9, that is GRPR is greater than 10 to the power 9. In the case of turbulent flow, you have to select the value of m equal to 1 by 3. The product of GRPR is called as Rayleigh's number, which is represented by Ra is a Gr multiplied by Pr. Characteristic length Lc represents here that dimension which is to be measured parallel to the boundary layer. In the case of vertical plate, we have a boundary layer will grow like this one. So this time we have Lc will be same as the length L. Same is true in the case of horizontal cylinder. Your boundary layer will grow on both sides. So we have Lc will be same as equal to L. In the case of horizontal cylinder, boundary layer will grow in this direction. So this dimension was measured parallel to the boundary layer, that is the characteristic length will be equal to diameter. And in the case of the horizontal plate, we have characteristic length will be equal to area upon perimeter. The forced convection equations are used in the case of heat exchanger. The very first equation you have to use the energy balance, that is the heat rejected by the hot fluid, which is given by m dot h Cph into Thi minus Tho, must equal to the heat gained by cold fluid, which is given by m dot c Cpc Tco minus Tci equal to U0 A0 LMTD. Here U0 is called as overall heat transfer coefficient based on outside area, and LMTD is a log mean temperature difference. Heat exchangers are classified according to the direction of flow of fluid in a double pipe heat exchanger as parallel flow, counter flow and the cross flow. In the case of parallel flow, both the fluid will move in the same direction, that is the hot and cold will move in the same direction. In the case of counter flow, the hot and cold fluid move in the opposite direction, and in the cross flow they are perpendicular to each other. In the parallel flow, the hot fluid enters at temperature equal to Thi and leaves at temperature equal to Tho. Cold fluid enters from the same side as the inlet of the hot fluid at temperature equal to Tci, leaves at Tco. The difference between Thi and Tci is called as the theta I is Thi minus Tci. Theta O is the excess temperature at outlet is given by Tho minus Tco. In the case of the counter flow, the hot fluid enters at temperature equal to Thi, leaves at temperature equal to Tho. Cold fluid travel in the opposite direction, enter at temperature Tci, leaves at temperature equal to Tco. So there is a change in the definition of theta I this time. We have theta I equal to Thi minus Tco, and theta O is given by Tho minus Tci. For all these equations here, we have LMTD is given by the difference of temperature, that is theta I minus theta O divided by natural log of theta I by theta O. And we have the LMTD of a parallel flow is less than the LMTD of a cross flow and is less than the LMTD of counter flow. That is for the same duty, that is a transfer, the area required for parallel flow is greater than the area required for cross flow is greater than the area required for counter flow. So counter flow is the most economical design for heat exchanger. So by default you have to always design for counter flow. There is a special case in a counter flow when the product of mass flow rate of a hot fluid and the specific heat of the hot fluid is equal to the mass flow rate of the cold fluid multiplied by specific heat of the cold fluid, that is called as capacity rate. In that case we have the theta I and theta O are identical value, and if theta and theta O are identical value, then the definition of LMTD will fail. In that case you have to use the same value of AMTD. That is, in this equation you have to replace LMTD by AMTD, and AMTD you can take as a theta I or theta O or theta I plus theta O divided by 2. If we have a counter flow and we have this condition, then both these lines are parallel lines. So this special case is called as the balanced counter flow heat exchanger. In this case the temperature profile will be parallel straight lines, that is you have to join Thi and Tho by a straight line, as well as Tco and Tci by straight lines. If one of the fluid changes its phase, then the direction of fluid does not matter. For example, evaporator and in the case of boiler. You can design on the basis of parallel or you can design it on the basis of counter flow. It does not matter if one of the phase will going to change. Whenever we are given the cross flow, in that case the LMTD of a cross flow can be calculated on the basis of LMTD of a counter flow. You have to simply multiply it by F, which is F is called as correction factor, and since this correction factor is always less than unity, so LMTD for cross flow is always less than LMTD of counter. If the tubes are very thin, in that case we can calculate the overall heat transfer coefficient based on outside area equal to 1 upon Hi plus 1 upon Ho. In addition to this, if you have given a fouling resistance from inside and outside, you can consider it, which is represented by RFI and RFO. The area A0 required for heat transfer is given by the surface area of one tube, that is pi d0L, multiplied by number of tube multiplied by number of passes. For single tube you have to use 1, for single pass you have to use 1. If you are given the number of tubes, then do multiply to calculate the value of A0. That is the total available heat transfer area. The second method used for designing the heat exchanger is net transfer unit and is given by A0 into U0 divided by C minimum. Here capital C is called as capacity rate and is given by watt per Kelvin. Is obtained by using the product of m dot multiplied by Cp. We have kg per second multiplied by joule per kg per Kelvin, which is same as watt per Kelvin. Ch is called as the capacity rate of a hot fluid, is given as m dot h into Cph, and Cc represents the capacity rate of cold fluid, that is m dot c into Cpc. Effectiveness is defined as the actual heat transfer divided by the maximum possible heat transfer. We have a actual heat transfer is given by m dot h into Cph, which is same as Ch into Thi minus Tho. Second value of actual heat transfer we can obtain as Cc into Tco minus Tci divided by the minimum value out of Ch and Cc you have to take in denominator divided by the maximum temperature drop, which is Thi minus Tci. Same is the denominator in the second case also. We have C minimum into Thi minus Tci. We get one more equation for actual heat transfer, Q actual. Now this time the equation is C minimum multiplied by Thi minus Tci. Second equation is Ch, which is same as m dot h Cph into Thi minus Tho. Third equation is Cc, which is m dot c Cpc into Tco minus Tci. And the fourth equation is surface area into overall heat transfer coefficient into LMTD. If you calculate the value of Ch and the value of Cc, and if Ch is less than Cc, then we have C minimum will be equal to Ch, and we have capacity ratio Cr is equal to Ch divided by Cc, that is C minimum by C maximum. If we have Ch is greater than Cc, in that case we have C minimum will be equal to Cc, and the capacity ratio will be C minimum, which is Cc maximum, that is C maximum, which is equal to Ch. And the special case is again we have Ch equal to Cc will be equal to C minimum will be same as equal to C maximum. This is a special case. In this case we have Cr equal to 1. The fourth case we have Cr will be equal to 0. That is one of the fluid has infinite capacity rate. So during the phase change process, that in the boiler and in the case of evaporator, we have value of Cr equal to infinity. Now there is a definite relation between effectiveness and NTU. In the case of parallel flow, we have a relation between effectiveness is given as 1 minus e to the power minus 1 plus Cr into NTU divided by 1 plus Cr. For counter flow, we have effectiveness is given as 1 minus e to the power minus 1 plus Cr into NTU divided by 1 minus Cr into e to the power minus 1 plus Cr into NTU. And if you have a special case in which we have Ch equal to Cc, in that case we have effectiveness is given as NTU upon 1 plus NTU. This relation is purely valid for counter flow. Whereas for condenser, since the direction does not matter, whether we have parallel or counter, we have only one equation, and this time we have effectiveness is given as 1 minus e to the power minus NTU. So whenever we have Ch equal to Cc, it means that we have Cr equal to 1. This time also if we have Ch equal to Cc, that is Cr equal to 1, in that case this 1 plus 1 become 2, and we have effectiveness equal to 1 minus e to the power minus 2 times NTU divided by 1 plus 1 will be equal to 2. The video you are watching is from the app, which is the More Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.